Okay, I will continue with the. I can say that is one of the most important part in CAGD, right? Is because it is the conversion. Right? Conversion or transformation is important because sometimes we want to transform from one model, a model that is more difficult to maybe to implement into another model which is simpler. Okay, for this example, we want to convert from Bezier curve to ball curve. So what should we do? So we can do the same thing like we have done with the Hermit curve, right? First of all, we have to equate. We have to equate two formula. The first one is the Bezier curve formula, right? And the second one is the cubic ball curve formula, right? Because we want to convert from one to another model, right? So we can equate, make it equal, make it equal, right? By this one is Bezier curve, this one equal to equate. This is cubic ball curve. Okay, we have to equate, and then we have to find what we call relationship between, okay, B0, B1, B2, and BT, right? V0, V1, V2, and V3. If we want to convert from Bezier curve to cubic ball curve, you have to know B0, B1, B2, and B3. It is given a set of Bezier control points. And then we want to find a sequence of cubic ball control points. We have 4 control points that will generate the same curve as Bezier curve, the same shape, exactly the same curve, right? So we have to find 4 unknowns, and we have known 4 variables. Okay, so we have to equate and find the relationship. Then when we equate it, or when we create them, right, both of them, so we have to expanding, right, and make it equal, expand the polynomial, right, because we want to rewrite this formula or rearrange in terms of t, which is, okay, in terms of t, B0 means t less to the power 0. Less to the power 0 means 1. Okay, we can eliminate it. And t square, t less to the power 3. Okay, we rearrange in terms of t raised to the power 0, power 1, power 2, and power 3. We can do the similar things to the cases of cubic ball curve, right? We can have, yeah, because these 2 equations are equated. These 2 equations are equated. So if we consider only the term t, so we can split this one equation into 4 equations. This is just one equation, right? But when we consider t raised to the power 0, t square, and t raised to the power 3, so we can have 4 equations. See, we can have 4 equations. According to T, this one is T raised to the power 0, T square, and T raised to the power 3. Okay, this one. We equate the coefficient of T. Make it equal, right? If the formula of T raised to the power T square, T raised to the power 2, sorry, T0, T1, T2, and T3, right? If we want to equate it, we have to check for the coefficients, their coefficients, whether they are equal or not. Okay, whether they are the same or not. So we can get these 4 formulas, and then we have to rewrite V, because we want to get V0, V1, V2, and Vt, right? So we have to write this in terms of B, B0, B1, B2, and B3. Okay, so we have to solve this system of equations. This is linear systems, right? So it's easy. Okay, so we can have we already have B0 is equal to V0. We leave this the same. Okay, and then we try to solve this system of equations by using B0 and V0, right? So when we do that, we can get B1 is equal to 1/3 V0 plus 2/3 V1. Okay, this one is a equation. This one is a B1 in terms of V0 and V1. And we can solve the the system of linear equation. We can get B2 and we can get B3. Okay, and this is quite I'm quite sure that this one is correct, because when we come up with B3 is equal to V3. So if you could remember the property of Bezier and ball curve, right? The first and the last endpoint the curve has to pass from the first and the last endpoint, B0 and B3, as well as V0 and V3. The curve has to pass the first and the last endpoint. Okay, so we have these 3 equations. These 4 equations. Okay, so we can see that this one is B0 is equal to 1 V0, and the rest will be 0, 0, and 0. And we have B1 is equal to 1/3 plus 2/3 multiplied by V0 and V1 respectively. And for B2, we also have the 3/3 B2, 1/3 T3. Okay, from this formula, actually, we can also write this in terms of the metric form. I'm going to show you later. But from these equations, this system of equation, we can conclude that each Bezier control point is a convex combination of a ball control point. Is it obvious? It is obvious, right? Bezier control point can be written in terms of convex combination. Why is convex? 1 plus 0 plus 0 plus 0 is equal to 1, right? And 0 is greater than or equal to 0. one is also greater than or equal to 0. So we can say that this one is convex combination, right? Each Bezier control point is a convex combination of ball control point, V0, V1, V2, and V3. The Bezier control points lie inside the convex hull of ball control point. This one you have to prove by go back to the previous slide. Right? You can see that this one is V0, V1, V2, and V3. Sorry, this one is V3. V3. Okay. What is a convex combination or convex hull of ball? Convex hull of ball is the yellow one. You can see that the pink one, which is the Bezier curve, right? And the blue one will be, no, I cannot use the blue one. I change it to green. Okay. The green one will be the convex hull of Bezier, right? Because this green one formed the Bezier curve. From the Bezier curve. So Bezier curve lie inside yellow one. Bezier curve, any point on Bezier curve lies on convex hull of ball curve. Okay, so you can see the conclusion. Bezier control point lies in the convex hull of ball control point. So it means that ball control point is bigger than Bezier. Right? Ball control point is around here. So it's bigger than Bezier curve, Bezier control point. Bezier control point approximate the curve better than ball. Also sure, because ball control point is closer to Bezier curve, right? So it can approximate the Bezier curve that is better than balls. And once again, ball control point is closer to the curve, compared to the ball curve. Okay, so from this formula here, so we can rewritten in terms of the metrics of conversion. Conversion matrix, right? 1 0 0 0 1 0 0 0 1/3 2/3 1/3 2/3 0 0 2/3 1/3 2/3 1/3 and then the last one is 1. Okay, we can write this in terms of the matrix conversion or conversion matrix. Matrix or conversion matrix. This conversion matrix will represent the relationship between side ball curve and ball curve. We can convert from ball curve into Bezier curve by using this formula. What if we want to convert from Bezier to one or to side ball? What can we do? Actually, we cannot just like this one is because it is a cubic ball curve, right? So we can say that this is a cubic side ball curve, or we can say that it is also cubic Wang ball curve as well, because they share the same formula, the same polynomials. If you use this metric as a matrix M, if I want to, okay, this is matrix M. If I want to convert from Bezier curve V1 V2 and V3 into one ball or side ball cubic Bezier curve. So if this is M, this will be M inverse. I can say that the conversion matrix is inversible. This one, conversion matrix is convertible. It has to be convertible because otherwise we cannot find M inverse. M inverse. How can I find the inverse of cubic from cubic ball curve to cubic Bezier curve or cubic Bezier control point? Anyone who can help me to get the result of M inverse of this matrix? We can use Mathematica in order to solve for this inverse matrix, but I'm not going to skip into Mathematica in order to calculate this, but I think you all can find this matrix. Okay, please try to solve this matrix and then write down it beside this one, so you can know that this matrix is a convertible matrix. Okay, this is just the conversion from Bezier to ball curve or from ball curve to Bezier respectively, but it is just only the cubic curve. Cubic curve means the highest degree is equal to 3. What if we want to find the generalization of the degree for the relationship or for the conversion from Bezier to ball? What shall I do? We can find from this formula. Okay, this is the formula for finding the relationship between Bezier and side ball curve, right? And if we want to find the similar things, the relationship between Bezier and Wang ball, convert from Wang ball control point into Bezier, you can use this formula. Okay, for the previous slide is to convert from okay, the previous one is the convert from Bezier, from the side ball to Bezier curve, right? To Bezier control point. The second one is convert from Wang ball control point, denoted by P, right? Bald P into Bezier curve, right? Bald B. Okay. This will be the exercises that you have to do, right? You have to write a program in order to find the relationship between Bezier and Wang ball curve of any degree. Also for side ball curve. Okay, please write a program.